Okay, so in this video we're going to be taking all of the structural analysis techniques that we've seen already and putting them all together and figuring out how we can derive a particular chemical structure from a set of data for a particular molecule. So we'll take combustion analysis data, percentages of each different element present. We'll take mass spec data, we'll take IR, we'll take the two sets of NMR data, and we're going to come up with a complete structure based on all of that. So what I want to do is to show you kind of the approach that you should take, all right? Things you can do to make your life easier. You know, for example, not starting with the NMR first, not starting with the IR first, starting with the combustion analysis first. All right, figuring out the molecular formula, figuring out the index of unsaturation, checking the molecular formula is right by the mass spec, looking at the functional groups through the IR, and then finally figuring out the backbone of the structure using proton and carbon NMR. So this is the order you want to do things in. So here is a example problem that we're going to look at. What we're given is a set of combustion analysis data. And the first thing we want to do is to figure out the formula that we're going to get from that. In fact, it's going to be an empirical formula. So you'll have seen how to do this. I'm not going to spend all that much time going through it, but you remember these are percentages. You can convert them into grams and then convert those into moles. So if you do that, what you end up with is something that looks like this. You get approximately 6.55 moles of carbon. You get approximately 8.25 moles of hydrogen, and you get also approximately 0.82 moles of oxygen. And of course, to get to the empirical formula, you just divide each of these through by the smallest, which ends up giving you a formula that looks like this: C8H10O. All right. So that's our formula, which gives us an empirical formula weight of, what is that? That's 96. That's 10. That's 106 plus 16. It gives us an empirical formula weight of 122. So it could be that the molecular formula is 122 or 244 or 366. Probably 122. But let's look at our index of unsaturation as well. We want to see if we've got double bonds or rings or whatever. So 8 carbons. The maximum number of hydrogens you can fit around 8 carbons is, well, CnH2n plus 2. If n is 8, that's 18. Minus the number of hydrogens you actually have in the molecule, all divided by 2 because of the fact that each unsaturation picks up 2 hydrogens, gives you 8 over 2, which gives you an index of unsaturation of 4, which should be an indication of something in particular. All right, it's pretty much always going to be benzene ring when you have an unsaturation of 4 or more. All right, okay. Now let's go back up and see what we got here. You remember we said we calculated an empirical formula of 122. Well, when we look at our mass spectrum, notice this is our parent peak, our M plus peak, is exactly 122, so therefore that's our molecular weight. And really, that's the most important thing we can get from here, other than, let's see, this is the base peak here, the most stable fragment, and usually you can get some information by just looking at the difference here. And you can tell there's a difference there of 15 units. And if you think, well, what group in an organic molecule has a mass of 15? Well, the only possibility is a CH3. It must have been a CH3 plus fragment in the mass spectrum. But what that tells us, not only do we have a molecular weight of 122, but in there somewhere, presumably on the end of the molecule somewhere, we have a CH3. That's some information that we didn't have before. That's one of the other useful things we can get from the mass spectrum. Okay. All right, so we've looked at the combustion analysis. We've looked at the mass spectrum. Before we move on, remember we said there was an unsaturation of 4, so we said there was a benzene ring. So right off the bat, we know that we have this. That's what we know. We have a benzene ring. And if all our unsaturations are used up, we also have an oxygen in there. And let's think about what functional groups do we know of that contain no unsaturations and only one oxygen. Well, there's actually only two possibilities. Those are either the alcohol or ether. So what we've done is actually narrow things down quite a bit. We either have an aromatic alcohol or an aromatic ether of some kind. We can actually tell which of those we have by looking at the infrared spectrum. Okay, let's just come down here. There is a bunch of stuff around here that's not of any real use. This very broad peak at around 1250, that is just a carbon-oxygen single bond stretch, which actually doesn't help us distinguish one way or the other, because you have the carbon-oxygen stretch in both the alcohol and the ether. What we are looking for is the distinguishing feature of the alcohol that's not present in the ether, which is that strong, broad OH stretch way down on the left-hand side of the infrared spectrum. And notice, boom, right there, that's what we have. That is highly indicative of the OH group. Alright, this is cool because now this tells us ether, we can say bollocks to you, we know we don't have you there, we know we have an alcohol. So, we know we have the correct molecular weight, we know we have a methyl group in there somewhere, we know we have an OH group. That is actually all we need to look at as far as the infrared spectrum goes, and we know we have a benzene ring. Alright, so we know we have OH and the benzene. But notice this is only 6 carbons. We had 8. And there's still a lot more hydrogens to figure out. Well, let's look at our proton NMR here and see what we can get. Now, there is one thing that should stick out like a sore thumb to you at this point. And that is what's going on in the aromatic region of the NMR spectrum. If you remember, that goes between about 6.5 and 8 ppm, which is right here. It's not so much that we have a set of peaks there, because we knew we were going to have that, because we knew we had the benzene ring. What should be of interest is their shape or multiplicity. Notice there are 2 2's here. Alright, and that specifies 2 separate peaks, 2 different peaks. One here and one here. Alright, if I just delete all that, it's extremely easy to get confused into thinking, well, actually, that's a quartet, isn't it? And actually, that would be fine if there was just one single number up above that peak. But there isn't one, there are 2. So therefore, we don't have just one set of hydrogens, we have 2. This goes back to what you saw in a previous video and what you may have seen in some of your questions before. That these are actually 2 doublets that are actually spaced very close together, looking suspiciously like a quartet. But those 2 doublets, now we know that that's what they are. You can only see those when you have this sort of splitting or this sort of substitution in your benzene ring, because you've got the hydrogens here that are the same as each other, splitting with the hydrogens here that are also the same as each other. Each is giving rise to one of these 2 doublets here. But then we've got to figure out, well, if I have 2 signals here, then I must have something here and something here that's different. So if I've looked at this, I can get rid of it. I also have this, this, and this. I got 3 peaks I haven't figured out yet. So let's see what we can do. The one functional group that we do know we have is the OH, is the alcohol. Now, which of these 3 peaks do you think would be the OH? Well, it has to be the one that has an integration of 1, unless there's more than one peak that has an integration of 1, and in this case there isn't. And notice also that this peak is kind of broad. That is broadened due to the OH equilibrating with water molecules inside the test tube, inside the tube when it's being run through the NMR. So that suggests the OH is somewhere in that molecule, and that's what this is. More than likely that OH is coming off one of these two ring carbons. But let's see if we can figure out what we have here. Now you may have seen this before. A triplet and a quartet pretty much always mean a particular functional group, but let's break it down and see. This quartet corresponds to 2 hydrogens, so therefore there's 2 hydrogens for this signal, 3 hydrogens for this signal. But the quartet doesn't mean 4 hydrogens. The quartet means N plus 1 is 4, N is 3, therefore these 2 hydrogens are next to 3 others. So therefore these 2 hydrogens must be next to a CH3. And in the same way, N plus 1 here is 3. So therefore N equals 2. And so therefore these 3 hydrogens must be next to 2 others, which must imply they are next to a CH2. This CH2 must be next to this CH3, hence they're being split by each other. And also think, which of these 2 is furthest downfield? Okay, well the one that's furthest downfield is the one that's closest to something electronegative, or could be the one closest to the benzene ring because of all its delocalization. And that's going to be the CH2 because it's furthest to the left. So what we can say is we have a CH2, CH3. We also have an OH. So what that means is then when we look at our final structure, let me just erase some of this stuff. You know what, let me do that bigger thing here. If I just erase some of this bollocks that we've looked at already. We said we had the benzene ring. We also said we had the OH. So let's see what happens. If we put the OH here, and then we say, well, if I put my CH2, CH3 here, this group and this group are different. Therefore, these hydrogens here, we'll call these HA, would be different to these here, which would be HB. So they'd split each other. Alright, the hydrogens for HA would be further downfield because they're closer to the oxygen, so therefore those would be HA. And these will be HB, more than likely. So this is our structure, but let's actually use the carbon NMR data to just check that we have this right. The first thing we want to do is to check that the actual number of signals that we have jives with what we have, what's in this data. So carbon NMR, we've got 1 carbon here. These 2 are the same, so that's 1, that's 2. These 2 are also the same, that's 3. These 4 is different, 5 is different, and 6 is different. So we should have 6 signals, and we do. We have 1, 2, 3, 4, 5, 6. Now usually in the carbon NMR spectrum, when you have peaks appearing between about 120-ish and 150, those are indicative of benzene ring protons, or benzene ring carbons. And they're usually present in sets of 4 or less, depending on what the substitution pattern on the ring is. There's also 2 more carbon signals for these 2. Okay. Now let me just tell you a little bit about what all this business means. Singlet, singlet, doublet, 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 triplet, and quartet. It doesn't mean quite the same as what it means in a proton NMR. In fact, I'm not going to go into the theory behind exactly what it means. I'm just going to go through how you can recognize what is what. When you have a singlet in a carbon NMR, that corresponds to a carbon that has no hydrogens on it. Alright, essentially N being 0. When you have a doublet, that implies a carbon with 1 hydrogen on it. A triplet implies a carbon with 2 hydrogens on it, and a quartet implies a carbon with 3. So therefore CH3, CH2, CH, CH, C, and C. So we should have 2 carbons with no hydrogens on them, and we have those in carbons 1 and 4. 1 being more downfield because it's closer to the oxygen. So this would be carbon number 1, that would be carbon number 4. For these two doublets, which would be HA and HB, probably the ones at 129 are carbon 2, the ones at 115 are carbon 3. And then when we look at 5 and 6, this is pretty much a no-brainer. This is a CH2, and it's more upfield than the last one, so that's 5. And that being a quartet, because there's 3 hydrogens on that carbon, that is it. So what we've shown is that that structure is the right one. What we've done is we've assigned an actual structure from all this data, and that is the way that you can go about it. All right, thank you.